Hello community, so great that you are back. Yes, today we talk about should I buy here a new NVIDIA machine here for AI reasoning? And you know what? I found here the solution today. It is absolutely premature. Let's have a look why. Welcome to the channel Discover AI, where we have a look at the latest of AI research papers. Let's just jump right into it. And here we have it. Also, it says October 12, 2025. It was just published yesterday, 21st of October 2025, and they talk about the limits of emergent reasoning in LLMs in agentic frameworks for deterministic games. And we have some beautiful ideas from our authors here of today's paper from Carnegie Mellon University, University of California, Berkeley, the College of New Jersey, and Algoverse AI Research. Let's have a look. Now, you know, just less than half a year ago, in June 2025, we had this publication by Anthropic. It was a counter-argumentation on the paper that there's an illusion of thinking. I mean, come on. And they said, hey, this is the illusion of thinking, because Mr. Opus, what a coincidence, told us here, well, no, our large reasoning model by Anthropic, they can reason. And you know what we found? If we now look in detail in this Tower of Hanoi game, that there is now a physical token limit to drive here the apparent collapse of our Anthropic models, of our Claude models. And they said, hey, the report collapse is exactly now explained here because we have only here 64K for Claude 3.7 Sonnet, and for the DeepSeek R1 we have 10K context windows. And this is why the models failed. But it is incorrect that the model cannot reason. It is just here this stupid 64K window. And you might say, wait a minute, if this is the argumentation, we can falsify it, no? I mean, we can verify it, no? So the authors of today's study said, you know what we're gonna do, we test this. We go also with the Tower of Hanoi, beautiful, we build an environment, now we have a multi-agent system now, and now we make it very easy, now. And we say, listen, if we have this problem here with a context window, no? Okay, let's ignore this. Let's build another solution. Let's say, rather than producing your entire solution trajectory here in a single generation of an Anthropic model, let's say our model must just act step by step, little baby steps, and just incrementally explore the state space. So everything else is done by other agents, here by the environment itself, and our little agent here just must reason. And we make sure that there's no limitation now from the token size of the context window. So we have our agent, we have here our strategy, beautiful, our Pi LLM here for the Tower of Hanoi game. We have the environment, we have here some API calls we can do, we have a validator, continue here, a guard, beautiful. Each move now is conditioned on the evolving puzzle state and all the prior actions, preventing now direct retrieval of complete solution, because, hey, we don't want that this LLM just goes on the internet and finds a solution, no? No, you stay with us here and you try to reason and you show us your reasoning process and we will evaluate your reasoning process. So what we do, say the authors, hey, we test now the pure reasoning capabilities of this Anthropic LLM, and great, and everything is done by the external environment. And so our little LLM just have to think. So let's see if an Anthropic model is really able to think. So at each step again, the model is given the system prompt, the user prompt, and the full history of the prior move. So it has the complete information. And it's only the environment that responds with a structured feedback after every tool call, such as the new state of the system. And of course, if we want to compare here probability distribution, we will be a little bit more intelligent, and we go not with a Kullback-Leibler, but with a Jensen-Shannon divergence, and I will explain in a minute why. But we have everything. This is absolute transparent. Read this paper. You're gonna love it. So we have here the system prompt of the Tower of Hanoi. So simple. And we have the user prompt. So simple. Plus, we have the complete GitHub. Here we have everything, analyze the agent, here analyze the agent policy, they analyze the subsequence, and everything is there. So I think it's time to start the experiment. Let's go. So at first, the old experiment, just an LLM and a large reasoning model without any agentic system, without any agent. Just the LLM. And you see, yeah, the number of disks here for our Tower of Hanoi game. And there's a harsh threshold here. And if we have 5 disks, we go from a success rate of 100% and we fall down here to, 24%. So, wow, this is now model collapse in reasoning. And we have here the full line is the Claude 3.7 Sonnet, and they use the exact same model, so there's no discussion, hey, this is a different model. And of course, it is not the current Claude 4.5, because otherwise, who would like to show that an actual brand new model has a malfunctioning in the reasoning capabilities? This would not be gentlemanlike. So we go with a Claude 3.7 Sonnet. And the thinking model has this dash line. Great. So thinking holds on a little bit better, but yeah, not really. And they also go here with the open source DeepSeek version 3 and a DeepSeek R1 reasoning model. Great. And as the complexity increases, you see as we move here on the x-axis here, more and more number of disks here, Tower of Hanoi, all the models thinking or non-thinking display a similar pattern. The success rate collapses when crossing a certain threshold. Here at about 4, here at about, maybe also 4, 5 disks. Great. Now this thing becomes interesting. Now we say, okay, now we are so much clever now, because now we go with agents. And we free up our reasoning agent that the agent has only to do the reasoning. Everything else is taken care of. So let's have a look if this agent, this anthropic model, can indeed reason. Again, beautiful. So here's now the agentic performance. What a difference. It is absolutely identical. At 5, we have here the breakdown, but now it goes down to 0. You say, wait a minute, hey, what? We go from 100 to 0? Within one disk? One additional disk? It's a little bit more smooth if you look here at the DeepSeek results. But yeah, of course our thinking model are a little tiny bit better. They hold on a little bit longer here on the thinking front, but otherwise you have a collapse here in the, if you want, success rate of the reasoning capability, of the solving capability of this anthropic model. And now it is, I would like to say, the genius here of the authors who provide us with an additional data. Because I ask myself, why we have such a discontinuity here at this particular threshold? What is happening here inside of our transformer model? And you know what? We have an answer provided by the authors. And they said, you know what? Here we have exactly the same. So at 5, here at this threshold, if we look at the loop rate, when the LLM goes back here in a reasoning loop, does not discover a new reasoning trajectory, but is repeating itself again and again and again. Look what happens here. We go from looping 0 to looping 100, exactly in this one additional number of disks. This is now interesting. Both agentic, but you see the behavior that happens now in the agentic models. Why suddenly we have here the reasoning collapse of the model? It seems not to be the 64K token context length. It seems to be something completely different. And of course, we have a DeepSeek version 3.1. Beautiful. Not so extreme like Sonnet, but also starting to loop. So what's happening? Yeah, they further give us information that 40% of the time the model deterministically reuses already previously observed continuations. Okay, forget about this. So we have a problem now. We have now the information here by Anthropic here from June. Hey, it was the physical token limit here to drive here the collapse of the model. And then we have this brand new paper that says, you know what? If we now go with a higher intelligence, now an agentic framework, the collapse is associated with failing to escape deterministic looping behavior of our anthropic models. And you might say, this is interesting, and you know exactly what happens if you have seen my last video on the dark shadow of artificial intelligence, that AI can deceive you, and maybe not only the AI. So let's have a look. With an increased complexity, the more number of disks we put here on the Tower of Hanoi, we see two primary behaviors of the model. No? The first is that the LLM, the parameterized model policy, diverges now from the optimal policy. I will show you this in a second. And the second is that the model parameter policy also diverges from the uniform random policy, any N policy. Now, the idea is that the collapse of the model is associated with one, two, or both of those behaviors. So let's do this, the author said. So we model out a decision making here of this particular anthropic LLM as a policy, our pi theta. Our LLM here, Tower of Hanoi, great. And we compare it now to the best solution, the optimal policy, pi star, and some absolute random uniform policy, pi random. And of course, since we have probability distribution, we go with the divergence, and we have to go with a Jensen-Shannon divergence, not with a Kullback-Leibler. I'll explain in a second. But it measures here simply the similarity between two probability distributions. This is what you already know. And here we have it now. This is here the GSD of our LLM-parameterized policy versus the optimal, and here versus the random. Do you see what's happening? Why GSD? Because Kullback-Leibler is not symmetric, and as I've shown you here in the proof at the beginning of the video, GSD is symmetric. So what we have? We have our policy in general, a probability distribution an agent uses to select the next action given the current state of the game. So we have now the real LLM policy, the probability it assigns to each possible move. This is if you want a subject under investigation, and then we have the optimal player here, 100% probability to the single correct move and 0 to all the others. This is our correct move. And of course, we have a random structure, no? The naive explorer policy. If you're stuck, you have to explore the solution space. So it assigns no equal probability to all valid moves. Let's say we have 3 possible valid moves, and it assigns now 33% to each of those 3 moves. This is the benchmark for the exploration of the solution space. So what does this graph mean? Random policy. So if we compare now here this divergence here between here we have given the random and we have here our real LLM, the question is more or less how different is the LLM strategy from just guessing randomly? And you see this here in orange for Claude 3.7 Sonnet and in blue for DeepSeek. Now what is the answer? As we see here, if the problem gets harder, the more we move here to the x-axis, the LLM's policy gets progressively more different from a random exploration strategy. You might say, yeah, but maybe it is converging now to the optimal policy. So then this would be a good behavior, no? Okay, let's look at the other graph here. This is now if you compare here GSD divergence to the optimal policy, no? So the question is now, how different is the real LLM strategy from the perfect optimal strategy for this particular case? And the answer is, as the problem gets harder, the LLM's policy gets progressively more different from the optimal policy. The LLM stops making correct decisions, and this is expected and confirms that the LLM, the model, is failing. So this is now a strange situation, neither random nor the best. The GSD of the optimal policy against the observed LLM parameterized policy noticeably increases with the problem complexity, means the model, the LLM, diverges progressively from an optimal behavior with the increased complexity. And if you do the same with the random policy, this also increases with the complexity, suggests that some of the probability weights, which are uniform for the random agents, are being reassigned unequally, suggesting that the LLM has priors about what actions to take or prune in certain states, and does not reason at all. This is a catastrophic image. So what we have, the simultaneously divergence from both the optimal and the random policy implies that the models, the LLMs by Anthropic, are neither reasoning optimal nor exploring effectively. Instead, what they're doing, they're executing some deterministic patterns that become increasingly maladaptive. Now we encountered a massive systemic problem. So there's no reasoning at all. Here a quote by the authors here. When the models, the anthropic models, return to previously visited states and they're looping, they consistently execute identical suboptimal action sequences. This repetition in the reasoning sequence occurs despite models having access to the complete interaction history. So they know that this is not providing them any good reward function. But they continue to do it again and again and again. So for the repetition at lower n values, while at high n, its tendency to decrease shows signs of a deterministic pattern throughout revisiting the same unique state. Not learning at all. Not reasoning or exploring new path at all. And now it gets even worse. This inability, the authors tell us here in this quote, this inability to vary its behavior upon encountering familiar states, even after experiencing negative consequences from identical previous trajectories, could imply that, and this is now very friendly wording, apparent reasoning is actually an execution of a fixed computational pattern. Anthropic LLMs are just pattern matching machines. Are they not at all reasoning engines? Then we have a sentence by the authors. The model's Anthropic LLM inability to generalize and learn from its history, learn from its long-term planning, or even correct its own prowess seems, and this is a very friendly wording, seems to affect the model's ability to perform in a dynamic environment, which have interactions that are outside of the model pre-training distributions. So, everything that is not in the pre-training established as a pattern, no emergence of reasoning, nothing. Just predetermined patterns. This is the reasoning we encounter. What a nice study published October 12, 2025. And if you think this is not clear enough, let's have this quote here by the authors. We examine the reasoning performance of LLMs here, both from the Anthropic and from DeepSeek, and in both the single pass and the agentic environments, across both, we find that there is a performance collapse. Emerged as a consistent pattern, and demonstrated that environment access does not delay or prevent performance collapse. So the explanation given by Anthropic here in June 2025 was maybe not the most correct explanation. And they continue to say, our findings reinforce that apparent reasoning ability is largely a byproduct of higher probability mode following rather than genuine reasoning. So just a pattern repetition machine from its pre-training. And therefore, ladies and gentlemen, we come now to the beautiful sentence. Should I buy for $4,000 here the latest NVIDIA machines for an LLM or here a generative pre-trained transformer model in general? Well, no, because they have not the ability to reason, as was demonstrated in this paper today. And you know what is so frustrating sometimes? It is the behavior of the GPT systems in general, Anthropic or whatever you take. So when a generative pre-trained transformer gets lost, when a decoder transformer part gets lost, its policy doesn't broaden or tries to explore. No? It's the contrary. The authors tell us it narrows down and it hardens into a very specific, very deterministic and highly confident, but absolutely wrong, set of actions. And then we loop in this wrong set of actions again and again and again. What a beautiful insight here from this study. And now we answer the questions. Can LLMs, and specific here generative pre-trained models here, reason or not? And the authors tell us here, they provide us here with a data-driven proof that this particular LLMs that they examined, when faced with a difficult, novel state, like this Tower of Hanoi game, doesn't get curious or think harder. The LLM doesn't try to improve and find solution. The GPT gets, this is not my wording, stubborn, and repeatedly makes the same mistakes again and again with high confidence. What a beautiful study. Have a look at this. We have Carnegie Mellon University, University of California, Berkeley. We have College of New Jersey and Algoverse AI Research. And you know what? You just need a simple idea. You just need a brilliant idea. Just one. to reveal a fundamental systemic flaw in all of the GPT system, in all of the large language model, and you can show that they do not have the capability to reason. I hope you enjoyed this video. I hope it was informative. You found something new. Maybe you want to subscribe. Maybe you want to even become here a member of my channel. In any way, I hope I see you in my next video.